Awesome. All right, let's take it away. So, hey, Mark, thank you. Um, like I mentioned, my name is Josh Etkind. I'm an aerospace developer on Meridian, and I'm going to talk to you about collision avoidance in Meridian. And that is, all right. So first of all, let's talk about what Meridian actually is. Meridian is our off-the-shelf flight dynamics in a box ground system. And the idea is that right out of the box, it meets 80% of your standard operational needs, with the remaining 20% achieved via working with our customers to configure and customize Meridian to model any sort of mission-specific parameters or additional free flyer mission plans that they might need. So that might include specific file interfaces, specific propulsion models, propagation parameters, force modeling, and fundamentally it is it's a thin client for free flyer mission plans under the hood. We'll get more into that a little bit more later. But the idea here is that with our decades of experience building mission-specific operations ground systems, we realized that we were duplicating about 80% of the software stack every single time. So Meridian represents a piece of software that can be mostly the same from mission to mission, but is tweaked and nudged to get it to conform to whatever your specific mission needs are. There's some screenshots on the right there. You can see it has a nice modern sleek design. And like I mentioned, we've got a lot of interfaces for maximum flexibility. Meridian right now is TRL 9 in both LEO and GEO. We are flying Landsat 8 and 9 and in LEO, and we're flying STPsat 6 out at GEO. And hopefully we'll be flying Zoom Chaser soon. So like I mentioned, Meridian is a web application, and the ConOps here is you have some external sources of data, you bring it into the Meridian ecosystem. Now, the Meridian ecosystem primarily exists as a web application. There's also a command line interface and some more software going on in the back end, but fundamentally you'll bring your external data in, it'll be stored within Meridian's internal database, and you can access it, manipulate it through the web interface, as well as send that data out to tasks. Now, tasks represent free flyer mission plans, which live under the hood. And as a Meridian operator, you don't really need to worry about how you're interacting with free flyer, because all of that is handled for you by the software. So you see a web application, you bring your data in, you operate on that data, produce flight dynamics products, and when you're ready to send them out to whoever your downstream consumers of flight dynamics products are, you can export those from the Meridian ecosystem to flat files, file shares, we can customize that to meet whatever your specific mission needs are for your ground system. Now, so the architecture of Meridian, we utilize containers and Docker specifically, and that lets us isolate all of our software from its environment so we can deploy the same components to all of our customers who have different equipment and different operating systems occasionally on their ground systems. There's a lot of technical detail, but the important thing is that Meridian exists, like I mentioned, as a web application. So as an operator, you go to a URL and you interact with Meridian just like you would any other website. Importantly, the containerization does allow us to deploy on air-gapped systems. So that is frequently what we do. We'll deploy Meridians to some local systems, and the operators can access it only within that secure operations environment. We also have a command line interface and interfaces directly to some other applications to support some of our power users. We also have an extensive automation framework, but that's a subject for a different presentation. So walking through a typical Meridian use case here, we're going to look at what you would do to do ephemeris generation within Meridian as an operator. So you would start with new GPS telemetry or maybe ground tracking data files. You bring those into Meridian via an import, and now those products would be stored within the Meridian database and accessible to the user and to all the tasks. The first thing you would probably do is run an orbit determination task to update your estimate of where the spacecraft is and where it was. You produce your latest definitive ephemeris as well as your latest definitive state vector. Then you'd probably bring those products into your maneuver planning task, where you would plan out any station keep maneuvers that you might need based on your updated estimate of where your spacecraft is. Once you have any maneuvers planned, you would bring those maneuver products, as well as your latest definitive state vector, over to orbit propagation, where you can model out to the future, predicting with a high fidelity force model the trajectory of your spacecraft, as well as the effect of any maneuvers. And orbit propagation will produce a predictive ephemeris. At that point, you would probably want to export your predictive and definitive ephemerides, as well as any maneuver notification files or other custom flight dynamics products out of the Meridian ecosystem to whoever the downstream consumers are of those products. So let's get into collision avoidance in Meridian specifically. The way we see collision avoidance working for an owner-operator is that they'll always be working with a screening organization of some sort, whether that's the 18th Space Control Squad, whether it's CARA, or any of the commercial providers that are still coming onto the market right now. And those screening organizations are taking care of some key tasks. First of all, they're performing catalog maintenance. So they're updating and maintaining estimates of however many thousands of satellites are trackable in relevant orbit regimes for your mission. They're also responsible for observation tasking. Let's say there's a conjunction identified that is of high interest and there's not great observations on the secondary object. Maybe they have some supplemental, some ground assets they can ask for some supplemental tracking on that secondary object. And they'll also be responsible for risk assessment. So understanding what the consequences of any conjunction would be, both for your asset and for other assets in your orbit regime. All of those responsibilities we see as staying with the screening organizations. And as an owner operator, you don't want to have to worry about that. You don't want to maintain a catalog of thousands of satellites. You don't want to have to deal with any of this. So you'll have a relationship with these screening organizations, and Meridian will help you interface with those screening organizations, as well as do some more things that we'll get into in a minute. So the primary way that we see this interaction working is as an owner operator, you'll be sending out predictive ephemerides as well as maneuver notifications to keep the screening organization apprised of your latest predicted trajectory and any maneuvers you might have planned. As the screening organization will screen those against the catalog, however many thousands of satellites they have in the catalog, and will reply with any conjunction data messages representing conjunction events that they have discovered. So where does Meridian fit in? Like I mentioned, Meridian is focused on empowering operators with some autonomy that they might not have otherwise. Whereas previously an operator might be limited to maybe some particular risk mitigating maneuvers that the screening organization sent over, Meridian will plan a wide variety of risk mitigating maneuvers and will give you some tools for visualizing the conjunction as well to understand both the geometry of the conjunction and how that evolves over time, how when you maneuver and with what magnitude you maneuver can affect the resultant conjunction. And all those tools are integrated into your flight dynamics ground system, which means that you can bring all the mission-specific modeling parameters and other mission priorities into that conjunction assessment process, into that process of selecting maneuvers to mitigate any potential conjunctions. Like I said, we support all the common export formats used by organizations out of the box, and we can customize Meridian to meet whatever import and export formats you need. We are catalog and screening provider agnostic as well because of that customizability. Yeah. So walking through the CA flow in Meridian, like I mentioned, you would start out with a conjunction data message representing one particular conjunction of interest. You would import that into the Meridian database where it will be accessible to all your tasks and to view. You'll then run the conjunction assessment task, which does a number of things, which we'll get into in a minute, but essentially what it's doing is giving you options for your risk mitigating maneuvers. Once you've selected a risk mitigating maneuver, which you're happy with, you'll bring it into orbit propagation, where you'll propagate out from your latest definitive state vector, including the effects of the RMM, and you'll understand how that RMM will affect the orbit of your spacecraft. You can look at its effect on your control box, anything else, and then you'll probably want to go back into your maneuver planning loop, where you'll replan any future station keeping maneuvers to incorporate the effect of the RMM. This loop you might iterate on this a few times. You might select a few maneuvers, screen a few ephemerides, and keep going. But eventually, you'll end up with an RMM that you're happy with, and a predictive ephemeris that models that RMM. So once you have those products, you can export them and send them off to your screening provider as a double check. So you'll notice that the idea here is that you don't have to cycle back and forth between your screening provider. Hopefully, the tools that Meridian provides will let you plan your RMMs with a little bit more autonomy instead of having to work back and forth with your screening provider a few times a day. So now we'll step through this process in Meridian, following along the steps in the slides as well. So the first thing we're going to do is ingest a conjunction data message. And some of this will be expedited for time as well. So to import a product to Meridian, this is Meridian. Here we're looking at the products page. Normally you would have all of your products listed here. So you see ephemerides, maneuvers, state vectors. The way that you import products is you go over to the import button. It brings up this wizard. You can, my mouse is being slow, but you can browse for a file. For the sake of time, I'm just going to speed through this a little bit and go select the conjunction data message that I imported earlier. So now this is representing the conjunction data message that I imported earlier, and all this data is stored within the Meridian database. It's accessible to any operator, but it's not. It's also immutable, so I can't, accidentally type a character here and mess up some important data. So on the overview page here, we have some information about this conjunction data message product. We have the particular spacecraft that it's associated to. We have the time of closest approach of the conjunction that it represents, the creation date for this product, as well as the missed distance at TCA. We have the state vector for the primary spacecraft at TCA. This is parsed from the CDM, so this might be useful if, say, you wanted to compare this against the latest predictive ephemeris to understand how well that matches up with your screening organization's prediction. And then we also have information about our secondary spacecraft or our secondary object. Here we can see the object designator, the name, whether that object is maneuverable. In this case, we're looking at a piece of frigate debris. We also see some parameters about how that object's orbit was generated. So this is some OD parameters. This is all parsed from the CDM, but it's easily accessible within the Meridian interface once that data is imported into the database. We also have the secondary object state vector at TCA here as well. So from here, we would probably head over to the conjunction assessment task, where we have a whole bunch of parameters that affect how the free flyer mission plan that will plan your risk mitigating maneuvers is actually going to operate. So first, we're going to select our spacecraft. This is going to send the spacecraft, all of its force modeling parameters, all of its configuration to the mission plan. We'll select an ephemeris from the database. This is our, in theory, this would be our latest definitive ephemeris, our latest predictive ephemeris. This conjunction is in the future. We'll also select our CDM that we were just looking at, and all this data will be sent to the free flyer mission plan. So what this mission plan is going to do is it's going to step through a series of epochs, and at each epoch, it will try to target a maneuver that brings the PC under a certain threshold. So that's what this threshold is. This hard body radius controls is a parameter of the probability of collision calculation. And when it's modeling burns, it uses a finite burn model within Free Flyer, and all of that propulsion modeling is configured within the spacecraft object, which is you can change a whole suite of things to change how the propulsion model is applied. But here we'll select a thruster set that we like and a tank set, as well as a command offset controlling what angle we're going to burn at. This task allows you to potentially screen 2 different burn configurations. So in theory, if you wanted to try a prograde burn and a retrograde burn, you could select different thruster sets or different command angle offsets. Here we're going to do a retrograde burn, so we'll yaw by 180 degrees before we burn. And these other parameters, like I said, are setting up that stepping of the epochs and figuring out how dense we want to target those maneuvers as well. So we would then send this task off to Free Flyer to go run. And here we're at the task summary page where we can see all of our parameters. For the sake of time, I'm just going to stop this task manually and head over to a task that I ran previously so we can see the output right away. So here on the task summary page, we have all of the input parameters that we used for this task. We can see any log messages that came from the task. We can see our spacecraft that we sent, the conjunction data message that we sent. These are our input products, and you can also see the output products. So this is all the data that came out of Free Flyer and lives in the Meridian ecosystem now. The first product we have is the collision avoidance maneuvers product. So here on the overview page, we have the spacecraft this is associated to. We have the source, which in this case is the task that just ran. We also have the time of closest approach and the probability of collision. This is a no-burn PC and a no-burn TCA that has been recalculated by the mission plan with our latest predictive ephemeris. On the maneuvers tab, we have a table of maneuvers that have been planned, which get us under that threshold PC at each of the epochs that we specified. So this table has a whole bunch of information, a whole bunch of maneuver options, and it'll tell you the burn duration, the epoch for that maneuver, the effective delta V, the PC resulting from that maneuver, the off pitch and roll angles, as well as a flag indicating whether that's the optimal maneuver, whether that's the lowest cost maneuver that was identified in this task run. So this CAM table is nice because you have all these maneuver options and they're individually accessible. But if you want to see general trends, we also have some plots, which is representing similar information. So here we're stepping along in time. This green line represents TCA, and here we're going to burn at each epoch and identify the burn duration, which got us below that threshold PC. So that's the red line we're looking at with our optimal burn indicated here in blue. And this is a similar plot, but showing range at TCA for each of those burns as well. And the other thing that we do here to help you visualize the maneuver trade space a little bit is a maneuver trade space diagram. And this is representing burning with, at each epoch, burning with a different delta V magnitude. And the color here represents the probability of collision resulting from that burn. So this is really the crown gem. This lets you understand where your options are, what are the low cost options, and identify some maybe counterintuitive trends or maybe not obvious trends within that, right? So without Meridian, maybe you would get an RMM represented something in this area, which says, okay, you're going to maneuver on August 16th at 0137 with a magnitude of 6.5 meters per second, and the PC will be 4.4 e to the minus 11 if you do that. All right, well, that's great, but maybe you burn a little bit cold, and then all of a sudden you wind up in this region over here where your PC is, in the e to the minus 4 range. But if you were to pick a burn of a similar magnitude at a different epoch, then you're much more safe. And you can also see these valleys where you can get away with a lower cost burn and a lower PC where you couldn't in other epochs. So this is a great way to visualize and understand sort of the options that you have as an operator. And once you're happy, once you've selected a maneuver, you would come back over to this collision avoidance maneuvers table, and you can, let's say we wanted to use our optimal burn, right? So we'll click over here, we'll click the plus maneuver button, and here we have this create maneuver dialog. So what we're doing here is we're creating a new maneuver product, which will be saved in the Meridian database, and all of these parameters are automatically populated from the data that came in from the last mission plan. So here we have a thruster scale factor, a burn duration, a delta V, a burn epoch, as well as all of our selections for our propulsion model, and we can just save this right to the database, and it'll be available for us to use in orbit propagation. So I think I talked through a couple of my slides here, right? So we ran through the CA task, we just created our risk mitigating maneuver, and now we will generate we can generate our orbit products. So we can head over to the orbit propagation task. We'll select our LEO spacecraft and grab that same definitive state vector that we were basing our predictive ephemeris off of that we used in assessment. We can head over to the maneuvers tab and select the maneuver that we just created. And so this will have now that maneuver is selected, it'll be modeled in our predictive ephemeris, and we can send this off to Free Flyer. And that is the more or less the conclusion of our CA process. So you would generate a new predictive ephemeris with that maneuver and a maneuver notification file. You can export those to whatever sort of formats or destinations meet your needs. Then you would send those products off to the screening organization, and you would probably come back in and replan any future maneuvers. With your maneuver planning task, which is in Meridian, you have your RMM that you selected, you have your latest definitive state vector, and everything is integrated and ready to go. So in summary, Meridian CA tool brings the CA and the RMM selection process into your existing flight dynamics system. So not only does that give you one data ecosystem, it also lets you leverage your own knowledge of your flight dynamics while you're planning your RMMs. Being able to dynamically produce RMM candidates and integrate them into your maneuver planning cycle allows you to iterate on that RMM planning cycle faster, because you don't have to send that RMM off to a screening organization to understand the PC. You can get at least a notional RMM in Meridian. We always recommend that you're going to send those maneuvers out to the screening organization for confirmation, but we think that it'll be more of a, this is what we plan, and they, usually they'll give you the okay instead of a, how about this, how about this, how about this situation. We also provide some unique visualizations to help you understand the dynamics of the conjunction, and this is all currently being validated in LEO via Landsat 9. So with that, I'll take any questions.
Cool. Thanks so much, Josh. That was a great presentation. We do have a couple questions for you. First off is, can Meridian provide CA for more than one spacecraft?
Yeah, absolutely. So you can, in Meridian, you can configure as many spacecraft as you'd like. So here we have, this demo mission is configured with one GEO and one LEO spacecraft, which would be a pretty unique situation, but you can create a new spacecraft and configure all of your modeling parameters to suit your needs. Like I mentioned, LMO, Landsat's mission operations, are currently flying Landsat 8 and 9 with Meridian. So they're flying Meridian with 2 spacecraft, and just like Meridian can support 2 spacecraft, conjunction assessment can do CA for 2 different spacecraft.
Okay, cool. And kind of following off of that, what probability of collision algorithm is used? Is it the same for LEO and for GEO?
Yeah, so right now our CA tools are only recommended for LEO. For LEO, we're using FreeFlyer's built-in PC method, which is a 2D PC, and that's great for high relative velocity conjunctions. But at GEO, I think there's a lot more worry about low relative velocity conjunctions, where that algorithm starts to break down. So I think for a GEO mission, we would probably want to customize that CA tool a little bit to integrate any other PC algorithms. Which is, I mean, one of the advantages of Meridian is that it's relatively easy for us to swap out a mission plan behind the scenes, and or even make a specific tweak for a specific mission to change change what PC algorithm you want to use behind the scenes.
Okay, great. Next is, so you mentioned there's the check mark in the results page of the CA for optimal maneuver. How do you define that optimal maneuver in Meridian?
Yeah, so this is it's definitely a notional thing. We're not doing any optimization. We're not we're not saying this is like absolutely the optimal possible maneuver for your mission. The optimal flag is an indication of all of these maneuvers that have been planned in this list, which one is the lowest delta V. And all these maneuvers are getting you below a PC threshold. So yeah, I mean, this optimal flag is a relatively unsophisticated portion of this. It's really just sort of a handy indicator for the operator.
Okay, and so is that a customizable aspect in Meridian? Can you choose what defines an optimal maneuver? If it's delta V, if it's PC value, if it's the lowest delta V with the closest TCA or something like that?
Yeah. I mean, with anything with Meridian is very customizable. So the it's a FreeFlyer mission plan behind the scenes. So anything that FreeFlyer can do, Meridian can do. Right now, the way that flag is set is there is a portion of free flyer code that looks at all the maneuvers we have planned and says what is the lowest delta V. So yeah, it would be really easy to change that to any sort of custom algorithm that you'd like to determine which maneuver is optimal.
Cool. And let's see. The last one is, so you had all the I think it was in the plot section, but yeah, the collision probability, that maneuver trade space, are the amount of maneuvers predefined? Can you define how many maneuvers you want Meridian to cycle through? How is that set up in the conjunction assessment task?
Yeah, so that is defined as a parameter in the conjunction assessment task. So this maneuver duration trade space will determine the lowest and the highest maneuver duration that you want to screen, as well as the interval between those maneuvers. So this example that you saw is a relatively high fidelity example where we maneuvered at a number of epochs. That epoch range is similarly defined by this evaluation period thing, which is the same control that determines the epochs that we're doing this targeting of maneuvers. You also have some flexibility about whether, if you include a retrobrain bird configuration, we give you the option to disable, in general, we give you the option to disable trade space plots because those do take a little bit to generate. We also give you optionality about overriding the propagator for those plots if you wanted to switch to a lower fidelity propagator, a higher step size, a lower tolerance for the integrator to generate those more quickly. I do actually have an example here of what one of those diagrams looks like with a lower resolution trade space. It's obviously less impressive, but it does run more quickly.